So hello everyone, good evening. So let us continue our discussion from where we left last week. So last week, as you all know, we just had a brief, introduction regarding the various concepts which we will be learning in this course. So from this week onwards, we will be going into detail. Okay. So the idea will be to understand the philosophies, the design philosophies, and its practical implementations as much as possible. Okay. So let us start then the second week lecture. Okay. So basically, now we shall be going deep into working stress method initially, and thereafter the coming methods. Okay, the limit state method basically. So say for example, this is a RC structure. Okay, so for designing this, we can apply various design method philosophies. Okay, so initially let us go for try to understand how the working by using working stress method. Okay, we can design. Okay, so what is its concept and how it is utilized. Okay, how it is implemented for designing. Okay? So if you see the IS code, basically you will find these values given. Okay, for direct tension, for M15 this is 2 megapascal. Okay, for M20 2.8, for M25 3.2, M30 3.6. So these are basically values. Okay, empirical values given for direct tension in the IS 456 code. Okay, which is the Bible for the reinforced concrete structure course. Okay, so yeah, apart from that, if you go to table 21, you will find the permissible stress in compression, bending compression, that is a sigma cbc values, the direct compression sigma cc, and the bond average. Okay, permissible bond average stress for plain bars in tension, that is the tau bd. Okay, so these values will find for 15 to 30. Okay, m15 to m30 at a range of 5, this one 5 megapascal. So M15, 20, 25, 30, you will find these values as per table 21, page 81, IS 456. Okay. Similarly, you will also find for the steel reinforcement the permissible values. So working stress basically is permissible. Okay, the permissible method of design. How much is allowed? Okay. So what we basically take as a safety. Okay, so this much is allowed. So that is the working stress. Okay. So in the case of steel, if you see for Fe250, okay, up to 20 diameter, so the tension will be 140 megapascal. Okay, tension strength basically capacity. The permissible stress basically. The compressive stress is 130. Tension is 140. Compressive is compression is 130, and shear is 140 again. For over 20 it will be 130, 130, 130 all. In case of Fe415, which is also the HYSD, that is high yield strength deformed bars, so it will have for up to 20 it will have 230 megapascal as tension, 190 megapascal as compression, and 230 megapascal as shear. And for over 20 it will be 230 again for tension, 190 for compression, shear 230 megapascal. Okay, so it is similar. Okay, and even in case of 250 also, leaving the tension and the shear part, the compression is similar. Okay, so these are the values you can obtain in IS 456. Okay, so you don't need to remember all those. Okay, so IS 456 is always allowed in exams and all, so you just need to understand the philosophies. Okay. So basically, as per that method, tensile stress, okay, this is equal to Ft by AC plus MAST. Okay, this is as per the working stress method. Okay, so here the Ft is basically the total tension on the member minus pretension in steel, because that will be balanced out already. Okay, during manufacturing. So that is basically the total tension on the member. Okay, reducing the pretension. That is the Ft value. AC is the cross-sectional area of concrete excluding any finishing material and reinforcing steel. Okay. M is basically the modular ratio, which is basically equal to ES by EC. That is elastic modulus of steel divided by the elastic modulus of concrete. Okay, we will be discussing in the coming slides. AST is basically the cross-sectional area of reinforcing steel in tension. Okay, so AC is concrete area cross-section, AST is cross-section area of reinforcing steel. Okay, yeah, so as I just discussed, modular ratio M is basically the ratio of ES by EC, that is the modulus of elasticity of steel, which is basically 2 into 10 to the power 5 megapascal, and modulus of elasticity of concrete, okay, EC, which as per IS code is 5000 square root of FCK. I think we discussed in the last class. So yeah, so using those values, you can easily find the ES and EC value, and using that you can find the M modular ratio, and this is required for the working stress method. Okay, why it is required? Because of this equation. Okay, so this equation is important. M is equal to 280 by 3 sigma CBC. Okay, where sigma CBC is the permissible stress in concrete during bending compression. Okay, so this value is highly utilized in the working stress method. Okay, so as we discussed last class, if we see this as a reinforced section, okay. So there are tensile reinforcements, because tension is always in the bottom, okay. Top it is compression. So tensile these are the tensile reinforcement rebars. So you can draw this diagram equivalently as this, like this, okay. So here basically, as we discussed, okay, so this is the effective cover from this portion to the middle of this rectangle. So if you see, this is the effective cover, that is the clear cover plus 5 by 2. Okay, 5 is the diameter of the river, so half of that distance, and adding the clear cover plus the clear cover, it will give you the effective cover. And clear cover is also known as the nominal cover. We discussed all those in the last class. So now let us go into the physics, okay, the physics and understanding of the this one, how like we calculate the forces and the capacity. So if you see, this is the cross section, okay. This is having a total depth of D, effective depth of small d, width of B, and these are the reinforcement. So if you see, we are, as I told you, always we calculate up till the effective depth, okay. So this is the extra factor of safety, okay. So here if you see here, so this is a strain diagram, this is the stress diagram, okay. So here if you see in the strain diagram at the topmost position, so this is epsilon CB, okay. So this is the maximum strain of concrete, okay, during bending, okay. And this is basically epsilon ST, this is the maximum tensile strain, okay, for the steel. So as per this one Hooke's law, okay, so epsilon CB is equal to FCB by EC, okay, because this is a straight line, okay. So therefore the stress will be directly proportional to strain, and the elastic modulus is the proportionality constant, okay. So that's why it will be directly epsilon CB equal to FCB by EC, and similar is the case with epsilon ST, which is equal to FST by ES, okay. So this is the strain diagram. If you go to the stress diagram, okay, so you will see that the topmost this one portion is FCB, that's why we use this for epsilon CB, and here it is the this one, the tensile force, okay, T, okay. So that is equal to FST into AST, okay. So here the force is also acting, the stress is also acting, so T is equal to FST into AST, okay. So we are basically assuming that the tensile force or the tensile strength is coming directly from the reinforcing bars, because concrete we assume is not good in tension, okay. And the compressive strength is basically directly coming from the concrete itself above the neutral axis, okay, because we assume that concrete is good in compression, okay. So if you see what is the total compressive force, okay, or the capacity, okay, of the concrete, okay, capacity of concrete in compression, so that will be as per this one, as per the diagram, it will be half into FCB into X, okay, for a unit width, for unit section, okay, like one section. For one section it will be half into FCB into X, okay. But we are taking like the section is having of this one width B, okay. So it will be multiplied by B, so this will be per unit width, and this will be the total compressive force, okay, or the capacity, okay. So that will be, we designate as C, okay, and this is, we are drawing reverse so that we denote that this is compression, this is tension, okay. otherwise it doesn't have any other significance. Okay, and this is the x is the depth of the neutral axis, okay, from the topmost, okay, from the compression side. Okay, so now as per this one equilibrium condition of the horizontal forces, so tensile force T is equal to compressive force C, so that will be the stable condition. Okay, and equating that, so this will be the stability condition, equilibrium condition. And if we assume x is equal to kd, okay, this x if we assume to as kd, what we find is, so this distance is basically called the lever arm. Okay, so the center of compression to the center of tension. Okay, center of tension is basically the middle of the rebar. Okay, that is the cc plus 5 by 2, gear cover plus 5 by 2. So this is the center of tension, but the center of compression we have to find out. Okay, so what is this distance from the topmost or the neutral axis, so we need to find this. But this distance center of compression to center of tension, it is basically called the lever arm. Okay, so that let us if we denote that like assume that to be j into t, okay, where t is the this one effective depth, so this will be equal to d minus x by 3. As you can see, this is d and this is x by 3, because as you told, as I told you, we need to find out. Okay, so because it is a triangle, so we know that centroid is always from the base, it is 1 by third. Okay, 1 by third of the height, so it will be x by 3. Okay, so now we can easily say it because it is a simple figure. Okay, the triangle. But when we go to limit state, we will see that it is not that simple. We need to mathematically calculate. Okay, so here it is good for us, so we can directly say it is x by 3, so it will be d minus x by 3. Okay, so this is d and this is x by 3, so this portion is d minus x by 3. Okay, that is the lever arm. So as we assume x equal to kd, it will be d minus kd by 3. And if we take d beyond the bracket, so it is d into 1 minus k by 3. So equating this and this, we find that j is equal to 1 minus k by 3. Okay, so that is the initial derivation. Okay, so uh, this is the basically the force. Okay, so now the main thing which we require while solving problems is the moment of resistance, that is moment carrying capacity. Okay, so that can be moment can be the resistance capacity can be can be found in terms of tension, that is reinforcement, as well as in terms of as well as in terms of compression. Okay, so that is concrete. Okay, so if we find in terms of in terms of reinforcement, it is m equal to t into jd. Jd is basically the lever arm, as we discussed just now. So t into jd, and t is basically fst into ast, as you can see here. So it is fst ast into jd, and m is basically C into JD. Okay, so JD is lever arm, so C is equal to half into FCV XB. So this is half CV X into B into JD, which if we solve properly, so it will come out to be like X is equal to KD, let us assume. So it will be equal to half FCB K into J into BD squared. Okay, and taking the half into FCB into KJ as R, we get this is equal to RBD squared. Okay, and R is known as the moment factor. Okay, and X equal to KD, Z equal to JD, and J is equal to 1 minus K by 3, as we just saw. Okay, so again equating T equal to C, we see that FST AST equal to half CB, half FCB into B into this one X or KD. Okay, or AST by BD is equal to half into FCB by FST into K. Okay, so this AST by BD, okay, so this AST by BD is nothing but the amount of steel reinforcement. Okay, percentage of, if you multiply by 100, it will be percentage of steel reinforcement. Okay, so we designate this this fraction as P basically. Okay, so we will be seeing this in coming classes, where they are using this P value for for designing and solving problems. And the I score also has this P value. Okay, so P is nothing but AST by BD into 100 basically. So because it is not 100, it is in currently in fraction. Okay, so P is in fraction, and this is equal to half FCB by FST into K. Okay, and yeah, so and yeah, P is also called the reinforcement index. Okay, so percentage of steel, it is basically the reinforcement index. And if you again equate even if solve further, we will find that FCB by FST, okay, that is the ratio of the bending in compression, okay, divided by the bending stress and compression of concrete by the strength of steel, okay. So we will find that is equal to 2p by k, okay, where p is in currently fraction, but if we multiply by 100 it will be in percentage, okay. So now for finding the critical neutral axis, okay, for finding the critical neutral axis, so basically we take the help of the strain, okay, in the working stress method basically. So in this working stress method, for finding the critical neutral axis, we basically equate the strain, okay. So we try to find the ratios, okay. So epsilon cb by epsilon st, okay, so that is basically using Hooke's law, it is fcb by ec by fst by es, okay. And if you solve it further, it will be fcb by fst into es by ec, okay. So this es by ec is nothing but the m modular ratio, okay. So it is the ratio of the elastic modulus of steel by concrete, okay. So it becomes fcb by fst into m. Also using the property of similar triangles, basically showing you, uh, yeah, so using the property of similar triangles, okay. So this is epsilon cb, this is epsilon st, and this is x, okay, and this complete is d, okay. So using the property of similar triangles, so what we see is this, yeah, so we see this epsilon cb, okay, by epsilon st, okay, that is basically nothing but x, this is x by d minus x, okay. So basically this theta and theta is equal, okay. So that is, and because it is small, tan theta is equal to tan theta, okay. So that means epsilon cb by d minus x is equal to epsilon st by, sorry, epsilon cb by x, okay, that is equal to epsilon st by d minus x, okay. So epsilon cb by epsilon st is nothing but x by d minus x, okay. So as you can see, epsilon cb by epsilon st is equal to x by d minus x. So x is equal to kd, so that means this epsilon cb by epsilon st is equal to k by 1 minus k, okay. So now this is one equation, this is one equation. If you know, as both are equal to epsilon cb by epsilon st, that means fcb by fst into m equal to k by 1 minus k, and therefore fst equal to m into fcb, okay, into 1 minus k by k, okay. So we find this equation. So this is very important equation basically. This is used for condition, this is the condition for evaluating the critical neutral axis, okay. So this is a critical neutral axis, okay. So if the neutral axis is less, the value of x is less than this, the critical neutral axis, then it will be under reinforced section, as we will find while we solve the problems. So problems we will find out. And if the neutral axis is less than the critical neutral axis, so it will be under reinforced. If the neutral axis is more than the critical neutral axis, it will be over reinforced, okay. So we will solve problems and find that out, okay. So let us continue the working stress method. So here basically, so this was a lump sum idea, okay. So basically this was the derivation, okay. So we will get more clear when you solve problems. So here basically in the working stress method, there are basic assumptions, okay. One assumption is that at any cross section, the plane section remains plane even after bending, okay. So that is in order to make the strain linear, okay, because the main concept is basically we are working in the permissible limit, that is till the proportionality limit, okay. So we are not utilizing the non-linearity, we are only till, we are using mainly the linear zone of the concrete and steel, okay. So for that to, you know, be that to satisfy, the plane section should, before bending, should also remain plane after bending, okay. Apart from that, all tensile stresses are taken up by reinforcement and none by concrete except as otherwise specified. So this point I mentioned just now. So the below portion, that is the tensile portion, is always taken by the reinforcement, okay. The tensile region is taken, the capacity is taken by the reinforcement. So we are like taking a very good factor of safety, okay, and not by concrete, we assume. And the upper portion basically, which is the compressive part, that is basically taken by the concrete, okay. So basically we are you know, underestimate the capacity, okay, and overestimate the loading conditions, okay. So the third point is that the stress strain relationship of steel and concrete under working loads is a straight line, okay. So that is what is the Hooke's law. Okay, so we are only taking the proportion. We are only working on till the proportionality limit. Okay, that is nothing but the working load or the permissible load. Okay, so beyond proportionality limit where the yielding occurs, we assume that the structure has it has fallen. Okay, so it has broken. Okay, so it has damaged. So we are not utilizing the non-linearity. Okay, so that is one of the disadvantage also. So this results in the uneconomic, okay, uneconomical section. But we have less confidence on the design, so that's why the working stress method basically only takes the permissible load or the working load. Okay, and apart from that, the modular ratio M has the value of 280 by 3 sigma CBC, which we just found out, and that is also equal to ES by EC. Okay, ratio of elastic modulus of steel by concrete. So as we just discussed, these are the values of direct tension. Okay, as per IS 456. These are the permissible stresses values in bending compression, direct compression, and bond. Okay, bond strength for plain bars in tension. So this is as per table 21 IS 456, and also these are the permissible stresses in steel reinforcement for tension, compression, and shear for FE 250 and 415 for 20 mm over 20 mm diameter. Okay, so this is as per table 22 IS 456. Okay, so we just discussed these values and tables. So this also in the diagram, the drawn diagram I just showed you. So x equal to kd, z equal to zd, j equal to 1 minus k by 3, m equal to 280 by 3 sigma cbc, c equal to half into fcb into bx, and t equal to fst into ast. Okay, m is equal to cz into cz equal to tz. Okay, so these are the equations, okay, and the derivations which we just discussed. So now let us see what is a balance section. Okay, so balance section is basically a reinforced concrete section. Okay, where the balance section occurs when the maximum allowable stresses in concrete and steel are reached simultaneously. Okay, so the allowable stresses in concrete and steel, when they reach simultaneously, that is called the balance section. Okay, and that will happen when the neutral axis is the critical neutral axis. Okay, so at the critical neutral axis section, the allowable stresses in concrete and steel will reach simultaneously. In case of under reinforced section, what is under reinforced section? So these are the sections in which the steel provided is less, okay, than the necessary for the balance section, and they are called the under reinforced section. So here the steel provided is less, okay, so they will basically fail first. So yeah, so that's why uh, the balance section, as compared to the balance section, the amount of steel provided is less. Okay, so therefore if you remember, the lever arm will be quite big, sorry, the neutral axis will be above the critical neutral axis. Okay, so therefore that will be the under reinforced section. Okay, so less amount of steel will be there in order, so that the steel fails first as compared to concrete. And what is the over reinforced section? What is the over reinforced section? So that is basically a section in which the steel provided is more, okay, than the balance section, and that is called the over reinforced section. So here the steel will be more, okay, and also the neutral axis depth will be higher than the critical neutral axis. Okay, so that will define the over reinforced section. For our practical purpose, we always go for under reinforced section, because the steel will fail first, and because steel is ductile in nature. Okay, it is not brittle as concrete. So what happens is we will see the failure occurring. Okay, so we can timely we can do, we can go for proper mitigation, okay, mitigation measures, and retrofitting measures at a timely manner. Okay, so it will not be sudden failure. Okay, so it will be time bound failure, and we can see the failure occurring. Okay, because steel is ductile. Okay, so that is the benefit of using under reinforced section. Okay, so yeah, so if we see here, so in the case of balance section, okay, so x by d minus x is equal to fcb by fst by m. Okay, so using this, as we discussed, okay, using the strain and the stress and the modular ratio, so this is the derivation. So this is equal to m fcb by fst, and kd, which is x, basically x minus this one d minus x by d minus x. Okay, so that is also equal to f m fcb by fst. Okay, so kd by d into 1 minus k is equal to m fcb by fst. So this implies that x by d, okay, so x by d is basically this is equal to k. Okay, so k is nothing but x equal to kd. Okay, so k is equal to x by d. Okay, so x by d is equal to k, and that is equal to what, mf fcb by fst plus m fcb. Okay, so that is a relation basically. So using this solving this, we find that x by d equal to k equal to m fcb by fst plus m fcb. Okay, and here m is equal to 280 by 3 sigma cbc. Okay, so that is the that is the case for balance condition. Okay, so using this only we find the critical neutral axis. Okay, so because it is a balance section, so we get the critical neutral axis, and here j is equal to 1 minus k by 3 as we discussed. So if you go to the tables, you will see that FCB is nothing but sigma CBC, okay, and FST is equal to sigma ST, okay, and for them various values are there. For M15, sigma CBC value will be 5. For M20, it will be 7. For M25, 8.5, and for M30, it will be 10. Okay, and similarly for sigma ST, for FE250, it will be 140 megapascal, and for Fe415 it will be 230 megapascal. Okay, so these are the values, okay, given in tables as per IS 456, and this k is equal to m sigma cbc by sigma st plus m sigma cbc as we just found out. Okay, and this m is nothing but 280 by 3 sigma cbc, which is the modular ratio, and that is equal to es by ec. So now if we using these two, if we solve further, we find this like this k is equal to m, which is basically 280 by 3 sigma cbc into sigma cbc. Okay, so this both of them get cancelled, and what is remain is 280 by 3. Okay, so that is nothing but 93.333. So k is equal to 93.333 divided by sigma st plus 93.333, and j is equal to 1 minus k by 3. Okay, and if we further assume this k, this is a capital K. Okay, so this is not different, these are different, not the same. So this k will be equal to kj by 2. Okay, so if we assume this, what we find is m is equal to capital K sigma cbc bd square. So if we have seen somewhere the equation, yeah, this one. So here m equal to half fcb kj into bd square, right? So if we take kj by 2 as capital K, so what we find is m is equal to capital K fcb, okay, bd square. Okay, so if you see here, so this is this fcb is nothing but sigma cbc, so capital M is equal to capital K sigma cbc bd square. Okay, so using this we can calculate the beam factors. Okay, so for Fe250 and grade of concrete M15, 20, 25, 40, this 25, 30, this K will be this one. Okay, so for Fe250 the sigma st value will be nothing but this one, 140, as you can see, 140. So using this 93.333 divided by 140 plus 93.333, so it will come as 0.4. Okay, so 0.4, and because Fe250 is there for all, so sigma st value will also be 140 megapascal, so it will be constant. Okay, so 0.4, 0.4, 0.4, 0.4. Similar is the case with j. Okay, so j is equal to 1 minus k by 3, so it is a function of k. So because k is constant, j will also be constant. Okay, so it will be 1 minus 0.40 by 3, which is nothing but 0.87. Okay, so 0.87, 87, 87, 87, so all are same. And in the case of k, okay, capital K, that is nothing but small k into small j by 2. So because k is constant, j is also constant, small k, small j both are constant, so capital K will also be constant. Okay, so that will be nothing but 0.174, 0.174, 0.174, 0.174, so all are constant. Okay, similar is the case with Fe415. So this was mild steel, this is high yield strength deformed steel. Okay, HYSD. So here also if you see, for here the small k value will for small k value sigma st will be 230. Okay, so because it is function of sigma st and that is constant, so it will be a constant value of 0.29. Similarly, j, because it is a function of k and k is a constant value, so j will also be equal to 1 minus 0.29 by 3, which is equal to 0.90. Okay, and because k and j both are same, sorry, both are constant, so capital K will also be 0.29 0.90 by 2 equal to 0.131 constant. Okay, so uh, yeah, so balance steel percentage is basically, as I told you, this is the reinforcement index, and this is equal to 100 into AST by BD. Okay, if 100 is not there, it will be in fraction. Okay, so therefore AST is equal to PBD by 100, right? And this X equal to KD. So this is the lever arm. Okay, this is basically the lever arm. This is the topmost compression part. So this is sigma CBC value. This is the center of compressive force. This is the center of tensile force. So equating the forces, we can therefore write half sigma CBC, okay, into X, which is KD, into B, is equal to AST into sigma ST, okay, where AST is PBD by 100. Okay, so this implies that P is equal to 50K into sigma CBC by sigma ST, and using that, okay, using that we can find the percentage of tensile reinforcement for balance section, okay, for varying grade and steel. Okay, so yeah, so for this we basically P, okay, P is the value which is calculated. So for that we need K, sigma CBC and sigma ST. Okay, so for this sigma CBC value, that is yeah, so that is given here. So it will be 15 is 5, 20 is 7, 25 is 8.5, 30 is 10. Okay, and sigma ST value, there are two values for 250 FE. To FE 250 it will be 140, for FE 415 it is 230. Okay, so what is remaining is K. K is dependent on sigma ST on, right? So for this one, yeah, so for this one K will be constant, and for this one also K is constant. So this K is this one. Okay, so for 250 it is zero point 0.4, for 415 it is 0.29. Okay, zero point 0.4 and 0.29. So using these values you get these values as the value of P, that is percentage of tensile reinforcement for balance section. Okay, for M15 and Fe250 it is 0.71%. Okay, for yeah, for M15 and Fe415 it is 0.31%. For M20 and Fe250 it is 1%. For M20 Fe415 0.44%. For M25 Fe250 1.21%. For M25 Fe415 0.53%. For M30 Fe250 1.43%, and for M30 Fe415 0.63%. So if you can see here, more is the grade of steel. Okay, sorry, more is the grade of concrete. Okay, so higher will be the percentage of steel reinforcement. Okay, and more is the grade of steel, lower will be the percentage of steel reinforcement. Okay, tensile reinforcement, because of the capability. Okay, high strength. Okay, so that is an important this observation, as you can see from the table. So yeah, so that is like for balance section we basically use the m value and the this sigma, the this value FST equal to m into FCB into 1 minus k by k. So this is the condition for evaluating the critical neutral axis. Okay, so now let us see how to find the actual neutral axis. Okay, so for from balance section we basically find the x by d value, which is the critical neutral axis. Okay, and how to find the this one, the actual neutral axis? For that we basically equate the compressive and tensile moments. Okay, so if you see here, so this is basically I have written here, given you hints how we have calculated. So moment is nothing but force into the lever arm. Okay, so lever arm is basically kd by 2 for this portion. Okay, and for this portion it is basically the this one d into 1 minus k. Okay, so yeah, so moment is not the lever, I'm sorry, it is the distance from the center of compression force to the distance between the center to the neutral axis for both the cases. So for compressive moment it will be force into this distance, which is kd by 2, and for tensile moment it will be this distance into this force into this distance, which is d into 1 minus k or d minus x. Okay, so The race part is basically the force. Okay, so force is what is force? It is nothing but area into elastic modulus into strain. Okay, in this case, because this strain is basically vertical. Okay, so because load is applied vertically, in this is a beam section, so load is applied vertically, so the strain is vertical. Okay, and because it will deform, deform equally, like the strain occurring here will be similar to strain occurring here. Okay, so therefore epsilon c and epsilon st will be equal. Okay, so these two will get cancelled, this and this. Okay, from both the portion these two will cancel. What will remain is AC into EC by AC into EC equal to AST into EST. Okay, here also if you see, this EC from here will go into here. Okay, so that is EST by EC, and that will become M. Okay, so what is remaining is AC, which is this portion. Okay, this is B into X. Okay, B into X. Okay, so that is the AC, and here AST is nothing but P into BD by 100. Okay, so that is the whole equation. So B into KD by 2 is equal to P by 100 into BD into M into D into 1 minus K. Okay, so yeah, so solving this equation. Okay, so we get K square plus P by 50 into MK minus P by 50 into M equal to 0. So here K is the this one, the variable basically. Okay, and it is a second order equation basically. Okay, so solving this and using the Sridharacharya formula. Okay, so we get K is equal to minus Pm by 100 plus square root P by 100 whole square into M square plus and this one uh, 2 into P by 100 into M. So solving the quadratic equation, we get K is this. Okay, that is minus B plus minus square root of B square minus 4AC by twice A, right? So it can be minus, this K can be minus, so we only take the positive value. So here P is equal to 100 AST by BD. So this is the whole derivation. So it may look tough, on face, as a face value, but if you go into detail, it is very interesting and you will love the subject. Okay, so using this, we can say that the moment of resistance basically M. Okay, so that is basically, if we calculate from the tensile part. Okay, so that will be AST into sigma ST into the lever arm. Okay, so AST is P by 100 into BD, sigma ST is the tensile stress, and D into 1 minus D minus X basically, D minus X by 3 basically. So that is the lever arm. Okay, so that equals to M by BD square equal to P by 100 into 1 minus K by 3 into sigma ST, right? So yeah, so that is all about the derivation. Okay, so now that is all about working stress method. Okay, so I have derived and I have taught you basics and understand it how to apply. Okay, so now let us see the application. Okay, so this is the first problem. Okay, so this is a singly reinforced concrete beam. Okay, singly because it is on the reinforcement is only present in the the tensile zone. Okay, if it is also present in the compression zone, it will be doubly reinforced. Okay, we will see this in later classes, basically coming classes. So here this is a cross section, okay, of our singly reinforced concrete beam. So here the width is B, which is 250 mm. The overall depth capital D is equal to 400 mm. The clear cover CC, okay, that is basically 25 mm. Okay, that is the distance from the tensile most tensile section, most tensile this one part to the outermost rebar. Okay, our distance to the outermost rebar from the bottommost part. Okay, so that is the clear cover, which is 25 mm, and the reinforcement is basically 20 diameter 20 diameter 20 mm dia bars of Fe 250 grade. Okay, and the grade of concrete is M20. Okay, so that is all about the data given. Okay, so basically we will find out various various parameters using this. There is no specific question as such. We'll basically try to find out various parameters using the information provided. Okay, and later on we will see the solved problems. There the question will be specific, what we specifically need to find, but this is just an example problem. Okay, so we will try to find out as many parameters as possible. Okay, so initially that is equating the tensile and compression moments basically. So what we did just here, okay, as I told you, that is the equating the compression and tensile moments about the neutral axis. Okay, So that is bx square by 2 equal to mast into d minus x. Okay, using this philosophy which I just explained you. Okay, just substitute kd as x because x equal to kd, right? So you will find bx square by 2 equal to mast into d minus x. So d here, which is the effective depth, that will be equal to 400 minus 25 minus 20 by 2, right? 400 minus 25 minus 20 by 2. So 20 by 2 is 10, right? So 25 minus 25 minus 10 is how much? Minus 35, right? So 400 minus 25 minus 10, that is 400 minus 35, which is 365, right? So it is 365 mm, right? And if you substitute these values here and other values as well, so AST is 5 into pi by 4 into 20 square, which is equal to 1570 mm square, right? And AST, we find out M is nothing but 280 by 3 sigma CBC, right? So sigma CBC for M20, it is as much as I remember, it is 7. Okay, so yeah, so 280 by 3 into 7, so that will be, I think, 13.33. Okay, so you check the table, so you will get that. And yeah, so other values, b is 250, we know this, 250, right? So 250 into x square by 2 equal to 13.33 into 1570 into 365 minus x, right? So that means x square plus, like if you solve this equation, it will again be a quadratic equation, okay, like this. And again, using Sridharacharya formula, you will find that x is equal to minus 167.42 divided by 2 plus minus square root 167.42 whole square plus 4 into 61,110 by 2, right? So ultimately it comes as x equal to minus 83.71 plus minus 261. So it can be negative. So minus 83.71 plus 261, that basically comes to be x equal to 177.29 mm, right? Now let us find out the moment. Okay, the moment carrying capacity due to the concrete failure. Okay, that is basically the concrete moment carrying capacity. Okay, so yeah, I mentioned it correctly. So for M20, the sigma CBC value is 7, right? So yeah, so moment is basically what, as I told you. So moment carrying capacity will be how much? It will be the compressive force provided by the concrete into the lever arm. Okay, so compressive force is half into sigma CBC into x into b, right? So b is 250, x we found out is 177.29, and sigma CBC is 7 divided by 2 into b is 365 minus x is 177.29 by 3. Okay, so solving this, we get this as 47.45 kilonewton meter. Okay, that is the moment carrying capacity of the RCC, if we consider due to the concrete. Okay, the concrete moment carrying capacity. Okay, through compression. Okay, and if we see the moment carrying capacity due to the failure of steel. Okay, that is the tension moment, like moment carrying capacity due to tension. Okay, so if we see this, so we find that yeah, so M2 is nothing but AST into sigma ST into the lever arm, right? As we discussed in the last slides. Okay, so this is M2 equal to AST sigma ST into lever arm. So for Fe250, right? Yeah, for Fe250, the sigma ST value will be 140. Okay, as we saw in the tables. So sigma ST for Fe250 will be 144 MPa. So AST, as we calculated, it is 1570 mm square, right? So we know almost, yeah, we know all the values. So M2 equal to 1570 into 140 into 365 minus 177.29 by 3, which comes out to be 67.23 kilonewton meter. Okay, so that means this moment carrying capacity of concrete, okay, through compression, which is 47.45 kilonewton meter, it is less than the moment carrying capacity of steel. Okay, which is through reinforcement. Okay, so tension. Okay, so that is, which is 67.23. Okay, so 47 is less. So that means yeah, so that means we can say that the, you know, the moment carrying capacity of the RCC section. Okay, so that is basically always taken as the lower. Okay, lower of the two. Okay, so we can say that capital M is equal to 47.45 kilonewton meter. So basically, when we are asked to find the moment carrying capacity of a RC section, reinforced concrete section, we need to find out the moment carrying capacity from the compression side or due to concrete failure, and also from the moment carrying capacity due to the tensile failure, steel failure, okay, from the tension side. And we need to find out both, and we need to find the minimum out of them, okay. So minimum of 47.45 and 67.23 kilonewton meter is 47.45 kilonewton meter, and the minimum value is taken as the moment carrying capacity of the reinforced concrete section, okay. So with this, we will finish the working stress method. Okay. Now let us enter the limit state design method. Okay. So the main limit state. Okay. So limit state design method, basically there are two. Okay. One is strength and one is serviceability. Okay. So where limit states are there. So one is strength basically, and other is serviceability. Under strength. Okay. So there are four limit states. Okay. So basically four, you can increase also. So basically four, those are axial tension compression, okay, shear, flexure, and torsion, okay. And for serviceability, those are this one, uh, your deflection and cracking, okay. So from strength, as I told you, axial tension compression, shear, flexure, and torsion, okay. Out of those, the flexure is a very important parameter, and as because it is a beam basically, so beam is mainly taking, the beam is mainly taking a load, in a transverse way, okay, in a what to say, in a vertical way, okay. So that is, the load is passing through the neutral axis, like in a the passing vertically perpendicularly to the axis of the reinforced section, okay. So that's why it will fail under mainly bending, okay. So because beam basically fails in bending is nothing but flexure. So we need to find out, we need to calculate everything in flexure, okay. So like main parameter in beam is flexure, okay. So limit state of collapse, let us see how to calculate in flexure. So here also we assume the following parameters. One is plane section is normal to the axis, which is normal to the axis, remain plane even after bending, right. So that is true for working stress as well as limit state. Okay? Second is the maximum strain in concrete at the outermost compression fiber is taken as 0.0035. That is the topmost part. Okay. So if you draw the beam section, the topmost part. So there the maximum strain in concrete at the outermost compression fiber. It is basically taken as 0.0035. The tensile strength of the concrete is basically ignored. Okay. So we don't consider the tensile strength of the concrete because we assume that concrete is poor in tension and good in compression, okay. And apart from that, the stress block may be assumed to be a rectangle, trapezoid, parabola, or any other shape which results in prediction of strength in substantial agreement with the results of test, okay. So based on the results of test, okay, the stress block may be assumed to be any shape, okay, rectangle, trapezoid, parabola, okay, as per the prediction of strength in substantial agreement with the test results, okay. Apart from that, the stresses in the reinforcement are derived from representative stress strain curves, okay, for the type of steel being used. So based on the stress strain curves for different types of steel, the stresses in the reinforcement are derived. And for the design purpose, the partial safety factor gamma m is taken to be 1.15. Okay. So as we discussed also last time, so these combinations and safety factors come into picture, okay. So it can be for load as well as material, okay. So mainly for the limit state, okay, we take partial, okay, and for the working state we take full, okay. So if you remember, for a working stress method, the safety factor was factor of safety was 1.8, okay. So this value is a partial value of 1.8, okay. It is a fraction value of 1.8, so that is why it is called partial safety factor, because we are actually we are very much optimistic with our structure, we are very much confident, okay. So we have reduced the partial the factors factor of safety, or we can say we have taken partial value of factor of safety, so that's why it's called partial safety factor, okay. So that is taken as 1.15 for steel, and you will find out for concrete it is taken as 1.5, okay. Apart from that, the maximum strain in the tension reinforcement in the section at failure, it should not be less than Fy by 1.15 ES plus 0.002. Okay, so that is the for concrete the maximum strain in compression is 0.0035. Okay, and for the tension, the maximum strain in the reinforcement at failure should not be less than Fy by 1.15 ES plus 0.002. Okay, here the ES value is constant, okay. It is 2 into 10 to the power 5 megapascal. So it is mainly a function of Fy, okay. That is the yield strength of the steel, okay. So these are the stress strain curves for the concrete. Okay, so as you can see, so these are the stress strain curves of concrete. So yeah, so this is the FCK value, which is the, as you remember, this is the characteristic compressive strength of concrete. Okay, after 28 days, and characteristic strength means the value below which only less than 5%, values are expected to fall. Okay, 95% times it will be higher. Okay, so that is the actual value. So if we divide that by 1, as I told you, partial safety factor for concrete is 1.5. So if you divide that by 1.5, it will become 0.67. Okay, and again if you divide 0.67 by 1.5, so this is 0.5 FCK, 67 FCK by gamma m, which is 1.5. So it will be around 0.446. Okay, so that will be 0.45 or 0.446 FCK. Now the question is why we divide two times. Okay, so the reason is this: we divide two times because we take into account two factors of two uncertainties. Okay, so one uncertainty is basically the uncertainty in conditions. Okay, the casting conditions. Okay, so how we are, like, where we are going to cast. Okay, so what will be the uncertainty? Will it be hot weather, cold weather? Okay, so will there be any disturbances, environmental hazards, anything? So we take into account material, we take into account site uncertainty. Okay, so site uncertainty results in this divide by 1.5, and the second 1.5, as you all know, it is divided because of the material uncertainty. Okay, so will the material be as per predicted? Okay, definitely it will not be. Okay, it will not be ideal, but the design is ideal, right? So in order to take into account the uncertainty in material, we again divide by 1.5. So 1.5 we divide two times. One is to take into to take into account the uncertainty in site conditions, and the other 1.5 is in order to take into account the uncertainty in material condition. Okay, so if you see here, what we see is the stress strain curves up till a point of strain of 0.002, the stress strain curve behaves parabolically. Okay, up till there, but after that, from 0.002 up to 0.0035, which is the maximum strain at the maximum, at the topmost fiber due to compression. So up till from 0.002 to 0.0035, it is it is found to be constant. Okay, so this is parabolic, and after that it is constant. That means stress is not increasing anymore. Okay, so this is stress strain curve for concrete. Similarly, these are the stress strain curves for cold work deformed bar. Okay, so here if you see, important point is that here the Fy, as here we divided FCK by FCK by the partial safety factor two times. Okay, here we divided first for 1.67, and then again we divided. Okay, so we will get 0.446. But here, contrarily, in contrary, if we see here, the division is not two times. Okay, here only one times. So if you ask why it is like this, this is because steel is manufactured in a controlled environment. Okay, whereas concrete is cast in uncontrolled environment. We generally don't cast concrete in lab. Okay, we cast in environment, like in real environment. Okay, so that's why here the material uncertainty, the site uncertainty is prevalent. But here, because the steel is manufactured in a laboratory, which is a control environment, so we do not have to, divide it 1.15 by 1.15 two times. Okay, so it is controlled, so the situations are ideal. Okay, so we only divide it for the material uncertainty, and that also because it is a lab control environment, so it is not 1.5, it is simply 1.15. Okay, little bit, error will be there. Okay, little bit uncertainty, not not that much as compared to the real environment. So that's why we divide only by one time. Okay, so yeah, and ES value is taken as 2 into 10 to the power 5 megapascal, as I told you. So this is the stress strain curve for cold work deformed bar. So apart from that, this is the stress strain curve. Okay, for a steel bar having a definite yield point. Okay, the ES value will always be same. So yeah, so if we now see, okay, limit state of collapse under flexure for singly reinforced section, we will see that this value, as I told you, this value it will come as 0.446 FCK, which is 0.45, nothing but 0.45 FCK. Okay, so this is 0.45 FCK. So as we discuss in this graph, okay, so it will be increasing after the stress will be increasing after up till 0.002, and after that it will be constant. Okay, so similar is the case here. Okay, so it is the stress is increasing after up till a distance of 0.002. So this will be, we will see in the coming slides. So it will be 0.002, and after that it is constant. Okay, so till 0.002 it will reach 0.45 fck, and after that it will be constant. So this portion can be taken as a rectangle and this portion as a parabola. Okay, so we will be seeing that how it is derived, and how solved it and find the capacity. Okay, so here as you can see, so it is not a straight line. Okay, unlike the working stress, because we are going beyond the working limit. Okay, beyond the proportionality limit. Okay, so that's why it is not a permissible design as the working stress was called. Okay, so it also takes into an account some portion of non-linearity. Okay, so that's why it is much more economical and much more realistic. Okay, and that is why it is currently used. Okay, and the working stress has been discarded mainly because of that reason, this reason. Okay, so yeah, so as you can see, the epsilon cu value is it is 0.0035. Okay, and the epsilon s value, this one, it will be wow, how much, 0.87 fy by es plus 0.002. Okay, so that is the epsilon s value. Oh yeah, it is mentioned here. So if we divide 1 by 1.15, it will be 0.87, right? So yeah, so as you can see here, and apart from that, the other things are almost similar. Okay, so like working stress only. So c will be equal to yeah, c will, yeah, here the c will not be that easy. Okay, we have to find out. Okay, we have to calculate. This will be rectangle, this is parabola, that's why they have not given it. And this ast will be single, this value, it's this will be how much, so sigma st into ast. Okay, sigma st will be fy by 1.15, that is 0.87 fy, and ast is ast. So this is t equal to 0.87 fy ast, right? So apart from that, if we, yeah, so here this is the case which I was talking about. So if you see here, uh, yeah, up till 0.002 the stress is increasing. Okay, after that it became a straight line. Okay, so it has reached saturation. Okay, so using this, if you see, if you want to find out what is the value of x, okay, till where the stress is increasing after that saturation occurs, so you will find, like, if using similar triangle philosophy, so 0.002 by say let's say y is equal to 0.0035 divided by x. Okay, so that means y is equal to how much, 0.002 into divided by 0.0035 into x, which comes out to be 0.57x, right? So this 0.57x is the distance where this the stress diagram becomes constant. Okay, so it is up till that it is parabolic. Okay, it increases parabolically. So up till 0.57x it is parabola, and this remaining 0.3x it is rectangle. Okay, so from this concept we can find out the total compression. Okay, so that is nothing but the total area of rectangle minus this portion. Okay, so total area of rectangle will be 0.45 fck into x into b, right? And this area will be as we know, area of lower parabola. Okay, the, like, the exterior parabola, it will be one third of this one third of the area, right? One third into base into height, right? So it will be one third into 0.57 x into 0.45 fck into it is, that is for unit weight into capital into b. Okay, to get the total force. So minus, subtracting the rectangle minus the outer parabola, so we basically get the value to be 0.3645 fck x into b. Okay, which is nothing, which we can write as k1 fck into x into b. Okay, and so yeah, so this point k1 is nothing but 0.3645. Okay, so where yeah, so dividing and multiplying by d, you get c equal to 0.3645 fck into x by d into bd. So k1 can be said to be coefficient in equation calculating total load carrying capacity of concrete under compression. Okay, so that is basically the coefficient. This is basically for representative terms. Okay, and for that is the k. Okay, k1 value. And apart from that, so we found that 0.57 is the distance till where the stress increases parabolically, after which it becomes constant. Okay, so now also we need to find out what is the depth. Okay, depth of center of compression. Okay, so that also we need to find out. Okay, so that can be found out using concepts of engineering mechanics. Okay, or mechanics concepts. So taking total area, like we know the this one, the actual the force. Okay, 0.3645 into fck into x into b, right? So that into x minus k to x. Okay, that is the moment. Okay, so into x minus k to x. So this moment. Okay, so that will be basically equal to what? It will be equal to 0.45 fck, right, into x into b. Okay, which is the it is the moment of this. Okay, minus the moment of this area. Okay, so this area is 0.45 fck into x into b into x by 2, and this area, for this area, it will be how much? One third into 0.45 fck into 0.57 x into b into 1/4 into 0.57x. Okay, so this 1/4 is basically, so this is basically a parabolic spandrel. Okay, and for this the centroid is basically at a distance of h by 4. Okay, so that's why it is, and because this is 0.57x, the h is 0.57x, so it will be 1 by 4 into 0.57x, the centroid. Okay, from the neutral axis, right? So this is, and this is as we all know, as we discussed here, it is 1 by one third 0.45 fck into 0.57 x into b, right? Yeah, this 57 x into b. So that's why this is, if you solve, it becomes 1 by 12.45 fck into 0.57 x whole square into b, right? So solving this, we find k2 is equal to 0.416, which is approximately 0.42, right? So yeah, so that is all about the that is the distance of the depth of center of compression from the topmost fiber. Okay, so yeah, so from this we also found the depth of center of compression, right? So uh, yeah, so this is 0.42 in the case of limit state method. For working state method, stress method, because it was a triangle, it was simply k2 was 1 by 3, that is 0.33. Okay, because it was a triangle, x by 3 basically, right? So yeah, so depth of neutral axis of a given beam. Okay, so from, again, from the equilibrium of forces, total tension T is equal to fst ast. Okay, and total compression C is equal to 0.364 fck into x into b, right? So equating, we get 0.36 fck into x into b equal to fst ast, and x equal to fst ast by 0.36 fck into x into b, and x by d equal to fst ast by 0.36 fck bd, right? So dividing both sides by d, we are getting x by d equal to fst ast by 0.36 fck bd, right? So now taking fst equal to 0.87 fy, we get xu by d is equal to 0.87 fy ast by 0.36 fck into bd, right? Yeah, so yeah, so limiting values, now let us see the limiting value. Okay, the limiting value of x by d in as per is 456. So this is the general value. Okay, so any section you can calculate. Now let us see what is the x by d limiting value. Okay, so limiting value is the neutral, like the critical value basically, right? So as per is 456, epsilon su is equal to fy by 1.15 es plus 0.002, where es is equal to 2 into 10 to the power 5 megapascal. So that means, from, if you see this diagram, xu by d, okay, that will be nothing but epsilon cu by epsilon cu plus epsilon sc. Okay, so that is from concept of similar triangle. Okay, so that is nothing but epsilon cu is taken as constant 0.0035 divided by 0.0035 plus epsilon su, which is having this value, right? So yeah, so based on that, epsilon su value will be this. Okay, based on the different fy value, mild steel, high yield strength, high yield strength. Okay, and these are the value of es, and xu by d, as you saw, like this is 0.00335 by 0.0035 plus epsilon su. Okay, so this value will come out to be 0.53 for mild steel, 0.48 for high fe415, and 0.46 for fe500. Okay, so these are the limiting values. Okay, or the critical values. Okay, So we can write C equal to K1 into FCK into X by D into BD, where K1 is, as we discussed, coefficient in equation calculating total load carrying capacity of concrete under compression, right? And K2 of X is the distance of the center of compression in the concrete from the top compression fiber. Okay, so from the top to the center of compression, this K2, which is 0.416 or 0.42 for limit state, and 0.33 for this one, working stress, right? So the maximum or limiting value of compression again, can be written as CL equal to F into FCK into BD, where F equal to K1 into X by D. Okay, from that equation, this equation. So yeah, so yeah, so based on this, okay, so based on this we can calculate the constants values, okay, for maximum compression block. Okay, so for Fe 250, Fe 415, and Fe 500. So because CL, okay, CL is basically F into FCK into BD, where F equal to K1 into X by D, right? So you can find out these values, okay? So for XU by D, 0.53, 0.48, and 0.46, K1 is having a value of 0.364, 364, 364, okay? So that this is constant, okay? So that is the total compression, that is coming from the equation, okay? Compressive force capacity carrying equation, okay, load carrying capacity in compression of concrete. So that is constant 0.364, and K2 is the, distance of center of compression from the topmost extreme topmost compression fiber. So that is also constant, it is 0.42 for this one. These two are constant for the limit state method, right? So using this and XU by D value, critical values, okay, a limiting value for 250 is 0.53, 415 0.48, 500 0.46. So we get capital F value as 0.192, that is K1 into XU by D. For Fe 250 it is 0.192, for Fe 415 it is 0.175, and for Fe 500 it is 0.167. Okay, now yeah, so expression of resistance moment for a balanced section in terms of Fy and P. So now let us see these values in terms of Fy and P. Okay, P is the tensile reinforcement percentage. So XU by D is equal to 0.87 Fy AST by 0.36 FCK BD. Okay, this is a very important equation. Okay, you should write it down in a notebook. So gate exams and all exams, various types of entrance exams always ask this question. Okay, so in terms of neutral axis or something limiting value or something. So mu is equal to 0.87 Fy AST into lever arm. Okay, we discussed. Lever arm is nothing but D minus 0.416 XU. Okay, so yeah, so D minus 0.416 into XU is what? It is 0.87 Fy AST by 0.36 FCK B, right? D is cancelled. So that becomes equal to D minus 1.005 Fy AST by FCK B. Okay, so 0.87 by 0.36 is 1.005. So if you sorry, 0.416 into 0.87 by 0.36 is 1.005. So if you take this as 1 only, so we get D minus Fy AST by FCK B, right? So mu will then become 0.87 Fy AST into D, okay, into 1 minus Fy AST by FCK BD, right? So that is the equation of mu. So yeah, mu is equal to 0.87 Fy AST D into 1 minus Fy AST by FCK BD. So mu is equal to, again, if we try to add this one, what is AST? AST is nothing but PBD by 100, right? So inserting a PBD by 100 instead of AST, we find mu equal to 0.87 Fy, okay, P by 100 into BD, okay, into D, okay, into 1 minus Fy by FCK, and AST by BD is equal to P by 100, right? So it becomes mu equal to 0.87 Fy into P by 100 into 1 minus Fy by FCK into P by 100 into BD square, okay, where P is equal to AST by BD into 100, right? So mu by BD square is equal to 0.87 Fy into P by 100, which into 1 minus Fy FCK into P by 100, right? So that is the equation of the moment carrying capacity. Okay, so please come in. So that is the, this is the balance section. So yeah, so this is the moment carrying capacity. Mu by BD square equal to 0.87 Fy into P by 100 into 1 minus Fy by FCK into P by 100, right? So now here, if we say what is the balance section, basically, so balance section is the section in which the tensile steel reaches yield strain simultaneously as the concrete reaches the failure strain. Okay, in bending. So that is the balance section. Okay. So here basically the yield strain on tension. Okay. It is reached basically together with the failure strain of concrete in bending. Okay. So that is the balance section. In case of under-reinforced section, these are sections in which the tensile steel reaches the yield strain at loads lower than the load at which concrete reaches failure strain. Okay, so yeah, so those are called the under-reinforced section. Hello, yeah, please come in the door. Okay, please come. Okay, I'm taking class. Yeah, yeah, yeah. So yeah, so under-reinforced section basically. Uh, it, So basically, yeah. So balance section is basically where the yield strain and the failure strain reach simultaneously. Okay, failure strain of concrete and yield strain of tensile steel. Okay. So in the case of under reinforced section, the yield strain reaches first. Okay. So it reaches first at a lower value, okay, then at loads lower than the load at which the concrete reaches failure. Okay, so yield strain reaches first as compared to the failure strain in concrete, so that's why it is under reinforced section. Okay, and in over reinforced section, the failure strain in concrete is reached the failure strain in concrete is reached earlier than the yield strain of steel. Okay, so mainly the concrete fails early at a time early than the yield strain of steel, so that's why it is over reinforced. Okay, so basically we need to see the failure strain of concrete and yield strain of steel. Okay, so if yield strain is equal to failure strain, it is balance section. If yield strain is less than yield strain is reaches yeah, if yield strain is less than failure strain, it is under reinforced. If yield strain is more than failure strain, it is over reinforced. Okay, so based on the equation we developed, okay, we can calculate the percentage of limiting steel areas for balanced design, right? For steel, Fe 250, Fe 415, and Fe 500. Okay, so X by D, it has values of 0.53, 0.48, 0.46, which we just discussed. So using that equation, which we derived, like this equation, right? Yeah, these equations which we derived. Okay, so from these equations, we find that yeah, PT into Fy by Fck basically. So that will be nothing but 0.36 by 0.87 into x by d into 100, right? So putting this equation, putting these values here, so we obtain the PT into Fy by Fck value, which is 21.97% for Fe250, 19.82% for Fe415, and 18.87% for Fe500. Okay, so yeah, so with this we will come to end of today's lecture basically. Okay, we will continue from here on in the next week. Okay, so now let us based on whatever we have discussed, okay, so let us try to solve a few problems, right? So yeah, so the first question is match the modular ratio to the respective grades of concrete using the options given, okay, given here. So list one is the grade of concrete, okay, and list two is the modular ratio, right? So for the grade of concrete, M25, M20, M15, M30. Okay, so we need to find the modular ratio, and we need to, yeah, we need to choose the correct option basically. So if you remember, modular ratio is nothing but M is equal to 280 by 3 sigma CBC. So for this one 15, it is sigma CBC is how much? 5. Okay, for 20 it is 7.5, for 25 it is 8, and for this one 8.5, sorry, and for 30 it is 10, right? So using that equation, you can 280 by 3 sigma c CBC, you can solve it, and you will find that M is 18.67, 13.33, 10.98, and 9.33. Okay, so from that you can see that M15 is 18.67. Okay, so M15 is 18.67. Okay, so C is 3 basically, this one. So other will be definitely this only. So M25 will be 10.98, M20 will be 13.33, and M30 will be 9.33. Okay, so basically A will be the correct option. So as you can see, A is the correct option, and this is the hint. Okay. Second question: consider the following statements. Okay, in an under-reinforced concrete beam, okay, the actual depth of neutral axis is more than the critical depth of neutral axis. In an over-reinforced section, the actual depth of neutral axis is less than the critical depth of neutral axis. Third statement: an under-reinforced section performs better on the ductility criterion. And fourth statement is, in a balanced section, both steel and concrete fails simultaneously. So which of the above statements is or are incorrect? A 2 only, B 1 and 2, C 2 and 4, and D 2 and 3. Okay. So in a balanced section, both steel and concrete fail simultaneously. So this is correct. Third statement: an under-reinforced section performs better on the ductility criteria. Yeah, because steel is ductile, and because steel fails first, so it will perform better on ductility. So third is also correct. In an over-reinforced section, the actual depth of neutral axis is less than the critical depth of neutral axis. So this is wrong. It is uh, more. Okay, so in over reinforced section, the depth of neutral axis is more than the critical depth. So 2 is incorrect. Okay, so out of all the four options, one will be correct. So in an under reinforced concrete beam, the actual depth of neutral axis is more than the critical depth of neutral axis. So this is also incorrect. In an under reinforced concrete beam, the actual depth of neutral axis is less than the critical depth of neutral axis. So 1 is also incorrect. Okay, so 1 and 2 both are incorrect. So B will be the correct option. Okay, so B is the correct option. So yeah, B. So in an over-reinforced section, the actual depth of neutral axis is more than the critical depth of neutral axis, right? Okay. Third question: consider the following statements. Statement 1: the behavior of an under-reinforced section is less ductile than an over-reinforced section. Statement 2: an under-reinforced section contains less steel and concrete, and concrete is less ductile than steel. Okay. So these are the two statements. Now we need to say which is true. Okay, 1 and 2 are true. 2 is and 2 is correct explanation of 1. 1 and 2 are true, but 2 is not a correct explanation of 1. 1 is true, 2 is false. 1 is false, 2 is true. So which is correct? Okay. So the behavior of an under-reinforced section is less ductile. So this is wrong. It is more ductile. Okay, because steel is failing first, and steel is a ductile material. So behavior of an under reinforced section is more ductile than an over reinforced section. So 1 is false, right? And 2, an under reinforced section contains less steel and concrete is less ductile than steel. So yeah, so under reinforced section contains less steel and concrete is also less ductile. Okay, it is brittle than steel. Okay, so statement 2 is correct. So statement 1 is false and statement 2 is true. Okay, so D is the correct option. So as you can see, D is the correct option. So yeah, so in under reinforced beam, the reinforcement failure occurs first, while in over reinforced beam, the concrete failure occurs first. Okay, since steel shows your significant amount of plastic deformation before actually failing. Okay, so it is more ductile. Okay, while as the over reinforced being brittle fails suddenly. So as you can see, plastic deformation of steel is more. Okay, so as it fails first, so it can be observed. Okay, so significant amount of plastic deformation can be seen, but whereas in case of over reinforcement, because concrete is brittle, it fails suddenly. So we don't want sudden failure. Okay, we want, you know uh, we want failure after a certain duration. Okay, so it should be propagated, time propagation should occur. Okay, so fourth question, let us see. Fourth question is, the dimension of a rectangular section is 250 mm by 350 mm. The clear cover is 25 mm. The tensile reinforcement is provided with three numbers: 16 mm HYSD bars. The grade of concrete used is M25. So which of the following is true for the section following working stress method? Okay, the section is an under reinforced section. The section is a balanced section. The section is an over reinforced section, or none of the above. Okay. So here, if you see, if you take the values, basically 250, 350, right? So and this one is 25 mm and the clear cover, and the diameter is 16 mm. So if you first find out the effective depth, that comes to be 350 minus 25 minus 16 by 2, it is 317 mm. Okay. Thus the tensile area of steel is basically 3 16 mm bars. So 3 into pi by 4 into 16 square, which is 603.2 mm square. Okay, Sigma ST, because it is HYSD bar, it is 230 megapascal, and M basically is 280 by 3 into, because 25 it will be 8.5. Okay, so 280 by 3 into 8.5, so it is 10.98. Okay, so M, as per the balance section, it will be M sigma CBC by sigma ST plus M sigma CBC equal to 10.98 into 8.5, which divided by 230 plus 10.98 into 8.5, which is equal to 0.289. So yeah, so that is the K value, right? So yeah, that is basically used for the this one, the critical condition. So actual neutral axis for this, we have to use the moment. Okay, moment about the neutral axis. So b into n square by 2 equal to m into ast into d minus n. N is basically the x value. So 250 into n square by 10 into 10.98 into 600, 3.2 into 317 minus n. Okay, so solving this quadratic equation, we get n equal to 105.79 mm and minus 158.77 mm. Okay, so n is basically the positive value taken, which is equal to 105.79 mm, right? Now, similarly, if we want to find the critical neutral axis, okay, so using this equation, which is basically the same here, nc equal to k into d, right? So yeah, so m sigma cbc by sigma st. Okay, so this is mainly found from the balance section condition. Okay, so m sigma cbc by sigma st is equal to nc by d minus nc. Okay, this implies that 10.98 into 8.5 into 317 minus nc equal to 230 nc. So this means nc equal to 291.5 millimeter. Okay, so here if you can see, this is the x value. Okay, so this critical neutral axis, it is less. Okay, or you can say the actual neutral axis is more than the critical. So when it is more, it is always over reinforced. Okay, so hence the section is over reinforced. So yeah, so C is the correct option, right? So yeah, C is the correct option. The section is an over reinforced section. Fifth question, the dimension of a rectangular section is 300 mm by 400 mm. The clear cover is 25 mm. The tensile reinforcement is provided with three numbers, 20 mm HYSD bars and M20 grade of concrete. Consider the following statements in regard with working stress method. 1. The effective depth is equal to 355 mm. 2. The percentage of steel provided is 0.86%. 3. The section is an under reinforced section. 4. The section is an over reinforced section. Which of the above statements is or are correct? A 4 only, B 2 only, C 2 and 4, D 1 and 3. Okay. So effective depth will be 400 minus 25 minus 20 by 2. That is 400 minus 25 minus 10. That is 400 minus 35. That is 365. Okay. So this is 355 mm. Okay. So that is wrong. Okay. So effective depth is 365 mm. So one is incorrect. So next is percentage of steel provided. Okay, so that will be how much? This will be 3 into pi by 4 into 20 square. Okay, divided by 300 into 365. Okay, whole into 100. Okay, so as you can see here, so this is 942.5 into 100 divided by 300 into 365, which is equal to 0.86586% only. So this is second is correct. Okay. Third is section is an under reinforced section. So for this we need to find out the neutral axis, both actual and critical. So actual, by equating moments, we get bn square by 2 equal to m into ast into d minus n. So b is 300, yeah, and we need to find out m is for, as it is what as it is m20, so it will be 280 by 3 into sigma cbc value is 7, right? So we get 280 by 3 into 7 equal to 13.33. Yeah, sigma cbc 7 megapascal. So m is 13.33, ast is 942.5, d is 365 minus n. So solving, we quadratic equation, we get 137.9 mm and minus 221.67 mm. We take the positive one, and from the balance section we find the critical neutral axis using m sigma cbc by sigma st equal to nc by t minus nc. So this is 13.33 into 7 into 365 minus nc equal to 230 nc, which where nc comes to be 105.34 mm. Okay, so as 137.9 mm is more than 105.34 mm, okay, so that means it is an over reinforced section. So as you can see, n is greater than nc, so the hence the section is over reinforced. So the section is an under reinforced section is wrong, the section is an over reinforced section is a correct. Okay, so 2 and 4 are correct. Okay, so C is the correct option. So as you can see, C is the correct option. Next question, 6. Following working stress method for sigma CBC equal to 8.5 megapascal and sigma ST equal to 280 megapascal, the ratio of neutral axis and effective depth, okay, of a this one of a rectangular section is how much? Okay, the section is 0.288, 0.362, 0.488, or 0.250. Okay, so we need to find out the ratio of neutral axis, the ratio of neutral axis and effective depth. Okay, as per the working stress method. So as per the working stress method, so this is the way of from the balance section. So we can find out the NC by D value uh, using the critical condition. So sigma CBC, it is 8.5 megapascal and sigma ST is 280 megapascal. So and because it is this one, sigma C is this one 8.5, so M will be 280 by 3 into 8.5, which comes to be 10.98, right? So NC by D equal to M sigma CBC by M sigma CBC plus sigma ST, which is equal to implies NCD by D NC by D equal to 10.98 into 8.5 by 10.98 into 8.5 plus 280. It is NC is equal to 0.25 D, right? So yeah, or D is the correct option, right? So yeah, D is the correct option. So seventh question, considering grade of concrete as M30 and grade of steel as 415, what is the ratio of the depth of neutral axis of a balance section as per working stress method to the depth of neutral axis of a balance section as per limit state method? Okay, and is it zero point 0.5, 0.8, 0.7, or zero point 0.6, right? So yeah, so for as per limit state method for Fe415, this is 0.48. Okay, x by d value, depth of neutral axis of a balance section. Yeah, so xu by d is 0.48, that is xu is this one 0.48, okay, for limit state design. And for working stress method, it is the last equation which you use, m sigma cbc by m sigma cbc plus sigma st. Okay, so sigma cbc for M30 will be 10, right? And m will be how much? 280 by 3 into 10, right? And the sigma st value for 415 will be 230, right? So if you see this, yeah, so this is 10, 9.33 is the m value. So NC by D is m 93.33 by 93.33 plus 230, where NC is 0.288 D. Okay, and as I told you, for limit state it is 0.48 D for Fe415. So dividing 0.288 by 0.48, we get zero point 0.6. Okay, so D is the correct option. So as you can see, D is the correct option. Next question, for the this one, for the steel grade Fe500, the maximum tensile strain permitted in limit state method as per IS 456-2000 is how much? A 0.0020, B 0.0042, C 0.0030, or D 0.0038. Okay, so as per IS 456, the maximum tensile strain permitted in LSM limit state method, it is, as you can remember, it is Fy by 1.15 ES plus 0.002. Okay, so that is equal to 0.87 Fy by ES plus 0.002. So Fy ES is 2 into 10 to the power of 5 megapascal. Fy is 500 megapascal, right? So it will be 0.87 into 500 by 2 into 10 to the power 5 plus 0.002. Okay, so yeah, so this is the this one formula. So using this, we get the strain in steel as 0.0042. So B is the correct option. So as you can see, B is the correct option. Ninth question, the limiting strain in compression fiber of concrete in limit state method of design is how much? A 0.001, B 0.0035, C 0.0003, D 0.0025. Okay, so as per assumptions of limit state method of design only, the limiting strain in compression fiber of concrete in limit state method is 0.0035. Okay, so limiting strain in compression fiber is 0.0035. So B is the correct option. So as you can see, B is the correct option. So you can refer to figure 21, okay, stress strain curve of concrete as given in page 69 of IS 456. Okay, and let us come to the last question of today. So as per the limit state method uh, of IS 456-2000, the assumed stress block for concrete is which one? Okay, A this one, okay, B this one, C this one, or D this one. So this is I think this will be correct for the working stress method. Okay, almost correct for the working stress method. But for limit state method, it is initially parabola up to a strain of 0.002, and after that it is constant. Okay, the stress is constant, so it is point up to up to a strain of 0.0035. Okay, so this is the parabola. Okay, parabola and rectangle. Okay, parabola and rectangle. So yeah, so the C option is the correct option. Okay, for limit state method. And the stress block for concrete for limit state method. So C option is the correct stress block for concrete, right? So yeah, C is the correct option. Okay. For this, you can also refer lecture 3 for the better understanding. Okay. So yeah, so with this we come to the end of today's discussion and problem solving. So hope you learned something from this discussion. So we will be carrying forward the discussion next week Sunday. So till then, best of luck and have a great week ahead. Okay, bye.